Great. So I'm going to go ahead and share my screen. That's okay. One moment. Adler, do you mind? Oh, there we go.
Great.
Okay. You guys can all see it?
Yes.
Great. Off to a good start. All right. So hello. I'd like to start by thanking all of my committee members for being here today, but I'd also like to take time and thank the rest of the audience for taking time out of their schedule as well. Today I will be presenting my dissertation entitled Machine Learning Methods for Causal Inference with Observational Biomedical Data. During my talk today, I'm going to share why causal inference is important, the role observational data can play in causal assessments, the complexities of such assessments, and a few new methods that I have developed to address these complexities. There are a lot of definitions of causal inference. My absolute favorite is by Voigt, and he very simply describes it as the process of drawing a conclusion about cause and effect relationships. So understanding the relationship between cause and effect is absolutely fundamental in a lot of disciplines, but none more so than in healthcare. Because in healthcare, we want to understand what causes serious high burden outcomes, and knowledge of what causes these outcomes supports our explanation and understanding of the phenomenon and informs our treatment and prevention of new cases. So in biomedicine, the preferred framework for causal inference is actually something called the counterfactual. Counterfactual reasoning leverages if clauses that are contrary to the truth to investigate what would have happened had the world been different. In this framework, we have the group itself, which is treated with the exposure of interest, and a comparator group that's the same in every way to the treated group except in the treatment itself. When we compare these two groups, we gain insights about the relationship between the exposure and the outcome. However, the counterfactual is only theoretical. It's never actually observable, a fact which is known as the fundamental problem of causal inference. But we can continue in our causal inquiries if we attempt to approximate this counterfactual. And we do so using something called the Rubin causal model. This model is an approach to counterfactual causal inference that's based on a framework of potential outcomes, which are outcomes in individuals of a cohort that could be potentially observed. Under Rubin's model, the outcome under each arm is given by the mean outcome of all individuals who are exposed to that treatment or the comparator. Causal estimates from this source are unbiased when two assumptions are met. The first is the stable unit treatment value assumption, or SUTVA, and this assumption stipulates that the outcome of one unit should not be affected by another unit's treatment assignment. This is assumed unless it's explicitly violated. And the second assumption is strong ignorability. And this assumption states that a unit's assignment to a treatment is not a function that is not a function of that unit's potential outcomes. So more simply, the treatment assignment is unconfounded and therefore it's totally ignorable. And this has a really important consequence of making features in both the treatment and the comparator arms equal in their distribution. But because SUTVA is assumed, we really just look to enforce strong ignorability in our data to produce good, solid causal estimates. So there are two sort of big umbrella approaches to enforcing strong ignorability in data. The first is randomized experimentation, which is the current gold standard in medicine. I call the resultant data from randomization experimental data. Of note, in biomedicine, randomization for causal inference is often done through the randomized controlled trial, or the RCT. This method is great because strong ignorability is theoretically upheld by the process of randomization, and it's highly regarded as reputable in the evidence-based medicine hierarchy. So for those of you that don't know, evidence-based medicine, or EBM for short, is the conscientious and judicious use of current best evidence from clinical care research in the management of individual patients. But randomized trial, like the RCT, may be expensive, it can be unethical, but most importantly, at least in my mind, they're blind to the subpopulation heterogeneity of treatment effect, which refers to variation in how subpopulations of patients actually respond to treatment. This can result in poor external validity, meaning the results of the trial won't generalize well to other populations, and can even induce new bias, which makes your causal knowledge potentially unsuitable for the practice of evidence-based medicine. The second option is the use of observational data that has been manipulated. And I will discuss what this means more in a second. But to clarify, observational data is data that is passively collected, meaning that there are no engineering adjustments. An example of this is the electronic health record data. So observational data has a lot of advantages over experimental data. There is a lot of it, which offers a lot of opportunity for pattern recognition. But in my mind, most importantly, unlike experimental data, it's much more likely to include a broad representation of our at-risk population, which makes inferences from this data source potentially more externally valid and perhaps more suitable for the practice of EBM. But the data is not randomized, meaning that it must be manipulated such that strong ignorability is upheld. So yes, observational data may yield more generalizable inferences, but its weaknesses complicate two central tasks of causality: the evaluation of existing causal knowledge and the generation of new causal knowledge. Today, I'm going to present my dissertation that addresses these two complexities of causal inference from observational data. My talk is going to be organized into the following sections. A brief summary of the literature review and gaps for this dissertation, the aims, of which there are 3, and significance and contributions of this work. I'm going to begin by discussing the literature review and the gaps. And this section is going to cover those 2 difficult causal tasks that I mentioned in the introduction section: evaluating existing causal knowledge and generating new causal knowledge. So when discussing the evaluation of existing causal knowledge, I specifically mean the ability to replicate causal estimates. Replication is an important component in medicine because, according to EBM practice, clinicians apply knowledge garnered from the RCT to the treatment of their patients under the belief that the intervention will show similar results in any population. So the effective and judicious use of causal clinical evidence is really predicated upon this assumption of replication. And if an RCT's effect estimate replicates in observational populations, the causal effect of the RCT would be perfectly valid. And we can compare these 2 effect estimates of these populations and provide a methodology to actually evaluate the external validity of these causal claims. So the RCT eligibility criteria should be sufficient to identify a real-world population in which the effect estimate will replicate what I call the applicable population. But the sufficiency of the eligibility criteria in identifying the applicable population is unknown. I'm going to address this unknown in aim 1 of my dissertation. Next, I'm going to discuss that second group of difficulties, the generation of new causal knowledge. There are a lot of different kinds of causal questions for generating new knowledge. So does X cause Y? Does A cause B more than C? And the type of causal question dictates our method of knowledge generation. So very 2 common types of causal questions include the comparison of an outcome between 2 cohorts and attributable risk estimation of exposures in a causal system. Recall that in the counterfactual framework, unbiased causal estimates require strong ignorability, and that this assumption enforces the empirical distributions of the features to be the same. This is also known as feature balance. But observational data must be manipulated in order to make this true. So if we have 2 cohorts or arms that we'd like to compare, but they do not have feature balance, which is shown here on the screen by color, that is, strong ignorability is not held, we can disproportionately consider units such that the resultant pseudopopulation does uphold strong ignorability. This procedure is called weighting. And after weighting, the feature in the comparator arms are distributionally similar and said to be balanced, and we can theoretically make unbiased causal assessments over this group. This is called a natural experiment, and that we've created a population in which units could theoretically be assigned to either the treatment arm or the comparator arm based on their features, which is very similar to what is imbued in an RCT. So inverse probability of treatment weighting, or IPW, is the most frequently used weighting method in biomedicine. And in this method, units are weighted according to the inverse of their probability of being assigned to the treatment, conditional on their measured baseline features. This is often called a propensity score. However, these weighting estimates are really dependent on the model used to estimate them, and the weights can be incredibly unstable or actually cause feature imbalance or bias if the propensity score is very close to 0 or 1. So a method that will learn feature balancing weights in a more model agnostic way is preferred. And I'm going to present a new method to fill this gap in AIM 2. Finally, the generation of new causal knowledge also pertains to the estimation of attributable risks, or ARs, of exposures in a causal system. So AR is the proportion of an outcome in a population that could be prevented by the elimination of a causal exposure from the population if there are no interactions between causal exposures and all other effects of exposures are removed. This is often framed as excess risk for an outcome and is summarized by the equation on the right-hand side of the screen. So ideally, estimation of ARs would be based on the knowledge of the relevant causal graph, in which the relationships between the exposures, the outcomes, and the confounders are made explicit. But in the setting of many potential exposures, this high-dimensional setting, causal graph construction may be infeasible. To estimate the ARs of many exposures simultaneously without knowledge of the causal graph, the primary question is really one of model specification. In this dissertation, I'm actually exploring the particular model specification for estimating ARs in the context of binary exposures and outcomes. So in this setting, typical methods of AR estimation include the calculation of excess risk by Levin, approximation using disproportionality methods for signal detection, such as risk ratios, RRs, or by the multi-gamma Poisson Trinker, MGPS, and regression-based methods, such as penalized logistic regression. In a perfect world, we would want a method of AR estimation that supports global inferences over the whole population, local inferences over just the individual, and has the ability to account for potential confounding. So the Levin definition and approximation by disproportionality methods are great at making global inferences of attributable risk, but lack the ability to make inferences for individuals. Furthermore, these methods are univariate and can't account for confounding. Regression-based methods are powerful tools for individual level inferences, but may often make global inferences that are unstable and lack interpretability as attributable risks. A model that can make all three of these estimations, that makes AR estimations that check all three of these boxes, would actually be greatly preferred. And I am going to present a new method in AIM 3, which does just that. So this dissertation addresses the three gaps that I briefly highlighted and investigates the replication and evaluation of existing causal knowledge with observational data and the generation of new causal knowledge with observational data, specifically pertaining to the comparison of an outcome between two cohorts and attributable risk estimation. So let's discuss our aims, my aims. I'm going to be presenting three aims today. The first one broadly addresses the evaluation of existing causal knowledge, and the second and third aim address the generation of new causal knowledge. Aim 2 specifically addresses comparing an outcome between two cohorts, and Aim 3 addresses the task of attributable risk estimation. I'm going to begin by discussing Aim 1. So this aim seeks to determine the feasibility of observational data to replicate causal knowledge. So in Aim 1A, I assess the ability of electronic health record data to replicate causal claims from an RCT, and in Aim 1B, I examine potential sources of residual bias in effect estimates from observational data sources. So RCT effect estimates are normally reported as a single metric and represent a weighted average of patients and their outcomes. So for example, we have these three patients here, and these are their frequencies of their effect estimates. And the reported RCT effect would have an average of their responses weighted by frequency, which would be about, right here. The ideal replication of this RCT causal effect involves identifying these correct patient subtypes in the correct proportions. The eligibility criteria should be enough to identify these patients because that's what practitioners have available to them. I am under the belief that the incremental addition of LRCT eligibility criteria to an observational cohort should make the cohorts increasingly more similar, thereby encouraging observational causal estimates to converge with that in the RCT. To add just a little bit more color to this, take a look at the figure on the left-hand side of the screen. So cohort A on the very top is very heterogeneous, and as we incrementally add eligibility criteria shown by the +1 on the side, we result in cohorts B and C, where we see the variability in patient type goes down with every new cohort. So in addition of each eligibility criteria, it will actually push the effect estimate of the cohort towards that of the RCT, which is shown at purple in the bottom of the screen. But whether or not this is true is actually still an open question, which brings me to my first aim, aim 1A. And in this aim, I ask, does the construction of observational cohorts according to RCT eligibility criteria encourage causal effect estimates to converge with that reported in the trial? To address this question, I propose the following methods, or I use the following methods. I constructed a baseline study population using Columbia University Irving Medical Center, or CUIMC, EHR data, according to an RCT indication. I use the RCTs by Hartley et al., which looks at sitagliptin versus glimepiride in elderly patients with type 2 diabetes. This baseline cohort was then queried multiple times, which each query being subject to the addition of a new eligibility criteria of the target RCT. Then with each incremental criterion, the unadjusted effect estimate and effect estimate adjusted by matching and stratification for an endpoint, I chose hypoglycemia for this example, were calculated. So to evaluate these methods, I then compared the observational effect estimate subject to all eligibility criteria with the effect estimate of hypoglycemia that was reported at the RCT's close. Here we can see the results of this sub-aim on the graph on the left here. So along the horizontal axis, the criteria are sequentially added with a legend on the right if you're interested. And the odds ratio is along the vertical axis. The solid horizontal orange line is the RCT odds ratio for hypoglycemia. And the solid purple, green, and blue lines are the effect estimates for the observational EHR data. The dashed lines correspond to the 95% confidence interval of each metric denoted by color. And we see that the increasing eligibility criteria, the observational estimate does trend towards the RCT. You can see that downward slope. But that despite adjustment by matching and stratification, the observational effect estimate was often marked with residual confounding that could not be accounted for. Which brings me to aim 1B. This aim addresses the question, why do observational causal effect estimates fail to converge with that reported in the RCT? I hypothesize that the residual bias between the observational effect estimates and RCT estimates, that green box that we saw in the previous results, is due to distributional differences in variables for which there's a heterogeneity of treatment effect. For example, consider an RCT effect estimate that's heavily dependent upon race, but the trial didn't specify race in its eligibility criteria. If in the RCT, the unmeasured distribution of race looks like something that's on the right here, this distribution may be necessary to replicate that effect estimate in any other population. But if we construct an observational cohort according to all the eligibility criteria at our disposal, we may end up with a very different distribution of races because this simply wasn't in the protocol. So an observational population may still be very different from the RCT population. And we can measure this directly through variables not in the eligibility criteria, such as race in our example here. So to address this hypothesis, I undertook the following methods. I created cohorts according to New York Presbyterian or NYP EHR data, according to the protocols of 4 trials: Accomplish, Renal, Prove It, and that Hartley trial from the previous aim. For each of these trials, I constructed 2 cohorts. The first was defined by the indication only, such as diabetes or heart failure, and the second cohort was the indication only cohort, further narrowed by all of the eligibility criteria that were available to us. Next, I queried the cohorts to obtain the Table 1 data and their corresponding RCTs. And by Table 1, I mean that baseline demographics table at the beginning of most trial publications. Things like age, blood pressure, blood glucose, etc. So the difference between the indication only and indication eligibility criteria cohorts versus the RCT patient cohort is going to be quantified according to these Table 1 patient characteristics. The continuous variables were compared by the standardized difference of the means, and discrete variables and proportions were compared by a point difference. So the results for any single trial might look something like this. And this is just a super small subsample to orient you to the data a little bit, where for every table 1 metric, like age, male or female, we get 2 values. We get the difference of that metric between the indication-only cohort and the RCT, and the difference of that metric between the indication eligibility criteria cohort and the RCT. So for each table 1 data point of each trial, I plotted these 2 evaluation metrics. So in any plot that's on the right of the screen, the difference between the indication-only cohort and the RCT is on the y-axis, and the difference between the indication eligibility criteria cohort and the RCT is on the x-axis. And this visualization allows us to better understand the patterns in the data. So in any single plot, a clustering of points near the center at 0.00 indicates that the observational cohorts differ very little from the RCT. Points that lie on the 45-degree line are indicative of baseline characteristics that are unaffected by the addition of eligibility criteria to the indication-only cohort. So deviations from this perfect correlation highlight the extent to which the application of eligibility criteria encourage or worsen the representativeness to the RCT, such as is in the case in the Accomplish or the renal trial. And high linearity of points suggests that the eligibility criteria do not identify a subset that are meaningfully different from the indication-only cohort, such as in the sitagliptin trial and the Prove It trial. Based on these results, the eligibility criteria that should be sufficient for identifying a population that would replicate, this may not actually be sufficient if HTE exists. If HTE exists and the differences we observed in our cohort are actually quite common, factors beyond the eligibility criteria may be necessary to identify applicable patients. And this finding has significant implications on how we create and apply biomedical evidence. There are, of course, limitations to this aim. There are fundamental differences that exist between the RCT and EHR data that make comparison between these 2 data sources difficult. The translation of all of those clinical trial eligibility criteria to operationalized queries may be prone to subjectivity. And finally, after subjecting an observational cohort to many, many criteria, the resultant cohort could be really small, which was the case in AIM-1A, likely eroding the stability of our causal estimates and producing underpowered results. Up next, I'm going to discuss aims 2 and 3, which address the generation of new causal knowledge. Beginning with aim 2, which pertains to the comparison of 2 cohorts. So in aim 2 of my dissertation, I'm going to present a method to identify natural experiments between 2 cohorts within observational data. In aim 2A, I develop a generative adversarial network that I call the counterfactual Chi-GAN to learn feature balancing weights. And in aim 2B, I apply this model to real-world observational data sets. So before I get into this method, I need to very quickly review what generative adversarial networks, or GANs, are. So these models simplify this really often troublesome task of modeling a generative distribution by pitting 2 neural networks against each other in a zero-sum game. The basic or vanilla GAN is shown on the screen, and it's comprised of a generative neural network, G, which takes samples from a target distribution, and a discriminative model D, which estimates the probability that that sample is real rather than generated from G. The goal of G is to produce increasingly convincing forgeries, and the goal of D is to become increasingly good at detecting forgeries. Ideally, at the end of training, G will win, and the forged samples are indistinguishable from real data. So the minimax game for this setup is given by the formula that's at the bottom of the screen. And I want you to note that this solution actually minimizes the Jensen-Shannon divergence. But this vanilla GAN architecture isn't going to suffice for learning feature balancing weights for a natural experiment, so we're going to need something new. Recall that in a weighting method with a treatment and comparator, our goal is to actually downweight individuals who appear too frequently in a single arm, so individuals who don't appear in the other arm. And what we want to do is we want to upweight people who do appear in the opposing arm, but their prevalence is not equal. In our case, with the treatment and comparator arms, after weighting, this upweighted population in the center could have potentially gone to either arm. And this is tantamount to the treatment assignment being effectively random, just like in an RCT. And this is that idea of a natural experiment. So this upweighted population is the group over which we can take unbiased causal estimates. So I imbued this logic into my model, the counterfactual chi-GAN, or the CGAN for short. And it differs from the vanilla GAN in two important ways. First, and most obviously, it is a single generator which feeds into two discriminators rather than one that we saw earlier. And these discriminators are sort of sit below the two populations that we would like to contrast. The second difference is that this model minimizes the chi-divergence instead of the Jensen-Shannon divergence. I use the chi-divergence because minimization of this results in minimal variance in important sampling estimates in downstream expectations. But using this divergence in our model requires a modification to the discriminator. So based on previous work by Noetsen, which specifies variational functions, we can take their change and easily incorporate this into the GAN objective function by just replacing the discriminators with Noetsen variational function. So these variational functions can then be evaluated directly to actually calculate the important sampling weights for each population. But for ease, I'm just going to refer to these as discriminators and denote them by D. So during the training procedure, for both of these populations, units are sampled from the treatment and comparator groups, so population 1 and population 2, and a complete set of features for each sampled unit flows downstream into their respective GAN. At the same time, the generator is going to produce a single set of simulated features, which is initialized with noise, and each discriminator then compares this to the unit's sample features. Over many, many iterations, the discriminators and generator will be trained such that features from treatment and comparator cohorts will become increasingly difficult to distinguish, or in other words, the features will be balanced. I can then directly evaluate the important sampling weights from each discriminator, remember as a byproduct of that variational function, and these can be applied directly to the features as a multiplicative to ensure that feature balance exists. So in aim 2A of this dissertation, I developed and implemented the CGAN and asked whether or not a GAN-based method can be used to leveraged to learn feature balancing weights. So in practice, development of the model and assessment of whether or not the CGAN can learn balancing weights is actually carried out through a simulation in which the ground truth is known. This involves constructing two cohorts in which there's sort of an overlapping proportion of the population, and we know what that overlapping population is. We then apply the CGAN and interrogate the weights of overlapping population and the non-overlapping population. So here's a schematic of the simulation that I implemented. I used two arms of the simulation, population 1 and population 2, but it is worth noting that this model can actually be implemented to inquiries between more than two groups. I began with 3 subpopulations, A, B, and C, which were drawn from randomly generated multivariate normal distributions, each comprised of 5 discrete and 5 continuous features. I constructed POP1 and POP2 such that part of both arms was born from the same subpopulation. So POP1 is a mixture of data from subpop A and subpop B, and POP2 is a mixture of data from subpop A and subpop C. 2,000 features were drawn from each subpopulation for each arm, so there were 4,000 units per arm. I also simulated a binary outcome, which was conditional upon the subpopulation of origin. And I just want you to make a quick mental note that the naive ATE from the mixture population, so just looking at POP1 versus POP2, is 50. And the ATE from the overlapping population, over which counterfactual inquiry is actually appropriate, that is just over subpop A, is 70. So also, just to make sure that this model is super robust and performant is consistent across all of these parameters that I've outlined on the right, I additionally conducted a sensitivity analysis in which I varied the per arm sample size, the unbiased average treatment effect that exists between subpopulation A in both arms, and the proportion of overlap. So to evaluate the simulation, I took many steps. I made multi-part. I made a visual inspection of the data, looked at the distribution of the weights by subpopulation. I inspected the convergence of features when weighted, checked the ability of the model to make the unbiased average treatment effect, or the ATE, and additionally inspected the effective sample size, or ESS, to make sure that there was nothing like mode collapse happening. And to contextualize the evaluation of the ATE and the ESS, I additionally implemented these comparator weighting methods. And I'm going to use these to contrast the performance of the CGAN. So here are a few results of the simulation. These are 2D projections of a few select feature combinations. I'm going to walk through these with you together, so don't panic quite yet. But just note that these images demonstrate the relationship between the setup of the simulation, the generator, and the weights. So this first plot shows the data for population 1, which is the orange dots, and population 2, which are the green pluses. In the second plot, I've highlighted the data generated from subpopulation A in purple. These purple areas denote the data that has feature balance between POP1 and POP2. In the third plot, I've taken a couple samples from my fully trained generator and plotted it over the data from plot 1, which is generator is in blue here. And finally, in the very last plot, I have the data from population 1 and population 2 that exists in the first plot all the way on the left. And I've adjusted the transparency by the normalized weights from the counterfactual Chi-GAN. So the darker or brighter the point, the higher the weight, and the lighter the point, the smaller the weight. And I hope you can see here that the region with the high weights is the same as the region of the generator, is the same as the region of subpopulation A. And this is compelling evidence that the structure of the model actually encourages the generator to identify the distribution that overlaps the populations, and also that the weights are learned such that units from this overlapping population have high weights. So just to demonstrate how the data changes over the training procedure, I've created this GIF for you. Again, this is just a random 2D projection. Blue is POP1 and green is POP2. I've adjusted the opacity of the points by the weight, and you can see here as the model gradually learns which points are from that same generative distribution and suitable for counterfactual inquiry. The GIF does repeat, so don't be alarmed if the points suddenly reappear. So if we take a look at the distribution of the weights by subpopulation, we can see that the CGAN actually learned weights for units that were generated from that shared distribution from subpopulation A versus those weights generated from other subpopulations, which were incredibly low. Prior to weighting, we also see great differences in the features between the mixture populations, just POP1 and POP2. And after weighting, we see that the differences in the features essentially disappear. This is that idea of feature balance that I've been discussing today. And when looking to evaluate the ATE, the average treatment effect, recall that by simulation, the naive ATE over just the mixture population is 50, but the ATE over the overlapping population in which counterfactual analysis is appropriate was 70. So to determine if the CGAN is actually better at estimating an unbiased ATE, I implemented the comparator weighting methods that are listed here, and I applied those weights to the outcome data to learn each model's average treatment effect. So those results are shown here, and you can see that the CGAN is actually nearest to the true treatment effect with an ATE of 70.01, which indicates that this model, the CGAN, may yield less biased effect estimates than its comparators. And if we take a look at the effective sample size, or ESS, we see similarly good performance. The CGAN has an effective sample size of about 3,870, and given that there were 4,000 units that were comparable across the two arms, each subpopulation contained 2,000 units, this is actually a very appropriate estimate. And in the sensitivity analysis in which I varied the parameters of the simulation, we saw similarly superior performance of the CGAN across both of these domains. So in AIM-2B, I applied the CGAN to real-world clinical data sets to answer the question, can this model improve feature balance for a noisy observational cohort? So to address this aim, I created observational cohorts according to the indication and intervention and comparator of published randomized clinical trial. I've again chosen the sitagliptin-glimepiride trial to present to you today. So for this experiment, as my features, I opted to use laboratory measurements with the least amount of missingness. When I plotted the frequency of these, there was actually sort of a hinge in the frequency of the labs, and I took the top 37 that were above this hinge. If there were repeated measurements, I took the most recent, and if there was missing data, I made a very simple imputation. I then applied the CGAN and all of the comparator methods from the previous AIM, which are listed here under bullet point 2, to this data that I collected. So to evaluate this AIM, I wanted to compare feature balance in the unweighted counterfactual, the counterfactual Chi-GAN and comparator weighted cohorts. And I quantified feature balance using something called the absolute standardized difference in the means, or the ASDM. Its name is exactly what it sounds like, but I've included a formula here on the screen for your reference. So a lower ASDM means that the treatment and control are closer to each other, or the treatment and comparator are closer to each other. And this is indicative of good feature balance between your arms. So in this plot, the 37 features that I mentioned are on the left-hand side, on the y-axis, and the ASDM is on the x-axis. Recall that the closer to 0 is better. So the per feature ASDM from data according to the CGAN is in orange. The unweighted ASDM is in gray, and all other comparator methods are in shades of blue. I recognize that this is incredibly hard to read, so I've actually summarized the mean ASDM across all of these features. So the unweighted ASDM for this experiment was 0.1103, and the CGAN produced the lowest ASDM of 0.0364. And this indicates that our method was best at achieving feature balance in this cohort. The CGAN and its related aims that I just presented, of course, do have some limitations. GAN training is known to be incredibly unstable, especially susceptible to small changes in tuning parameters. So given that the CGAN is architecturally much more complex than traditional GANs, it's reasonable to assume that training may suffer compensatory limitations in this as well. Additionally, assessing convergence on GANs is really not a standardized procedure. And in the best case scenario for the experiment in 2B, what we'd want to do is actually compare CGAN weighted ATE with the gold standard, which would be the randomized control trial. However, we found that the experimental setting from the RCT was so markedly different from our observational data, notably in things like the distribution of gender and race. If the variables with different distributions, if these elicit the heterogeneity of treatment effect, then effect estimates between these two data sources would just never be comparable, which is in fact what we found. So finally, I'm going to be discussing aim 3. In aim 3 of my dissertation, I address the generation of new causal knowledge, specifically with regard to attributable risk estimation. In aim 3A, I implemented a probabilistic model that I call the noisy or risk allocation, or NORA model, and I developed inference procedures. And in aim 3B, I applied the model to observational data sets. Recall that attributable risk, which I discussed in the introduction section, is the excess risk of the outcome owing to an exposure. In the setting of binary exposures and outcomes in which causal graph construction is infeasible, I mentioned 3 major groups of AR estimation: the Levin calculation, approximation by disproportionality methods, and regression-based methods. Additionally, I recall that I mentioned that there was no single method that was able to provide global inferences, local inferences, and was multivariate to account for confounding. To meet all 3 of these needs, I developed a method called the noisy or risk allocation, or NORA, which is presented on the screen right here. So NORA is a Bayesian probabilistic model to support attributable risk estimation in a cohort with a single binary outcome and multiple binary exposures. This model is an auxiliary variable representation of the noisy OR gate, a simple example of which is actually shown on the screen on the right. So a noisy OR gate is noisy because there are multiple exposures which have varying attributable risks. And it is an OR gate because we specify a gating rule which states that the outcome is present if any exposure is present. So E1, E2, or E3. This formulation captures the notion of causal independence both in the noisy gate, OR gate, and secondarily in NORA. And this assumption means that the probability of surviving an outcome given any exposure is independent of the probability of surviving given other exposures. More simply, it's something like taking drug B does not influence whether drug A causes the outcome. So NORA is a graphical model, as represented on the screen here. And I just want to orient everybody to graphical models really quickly. The nodes or circles represent variables. The edges or arrows represent relationships between the variables. Shaded nodes are observed and unshaded nodes are unobserved or latent. There are n number of people and k number of exposures. Note that the multiple exposures is where the noisy part of the noisy OR gate is captured. So in this model, exposures are given by X, outcomes are given by Y. This is where that OR gate is captured. The risk of any exposure, K, is given by R. And the activation for an exposure on an outcome for any person is given by Z. So in order for an exposure X to contribute to an outcome Y, it must be both present and active. And the activation of any risk for any person is dependent on both the presence of X and the magnitude of the risk, R. The only one activation is actually necessary for the outcome to occur. And again, this is sort of that idea of the OR gate coming around again. So in this system, the unobserved variables R and Z are learned through a Gibbs sampling procedure, and alpha and beta, which are the priors on R, are going to be learned through a Metropolis-Hastings algorithm. So in posterior inference of the activations of those Z's, we can actually infer which exposures are causal for this particular patient and a particular outcome. These are local inferences. And based on those inferences, we can also infer overall population level attributable risks for an exposure causing an outcome. These are global inferences. And because this is a multivariate setting in which we look at many exposures at once, this model is able to actually account for observed confounding. And these three things, as I'm sure you'll recall, are those criteria of attributable risk estimation that I just mentioned a few slides ago. So in AIM 3A, I implemented NORA and developed efficient probabilistic inference procedures. To begin, I wanted to know if NORA would produce causal risk estimates that were less biased than other state-of-the-art methods in this setting. So like with the counterfactual Chi-GAN, development of the model and inference procedures is actually confirmed through a simulation in which the ground truth is known. To address this, I implemented a simulated causal system in which the ground truth risks are known, and then applied NORA and the comparator logistic regression to estimate risks of our hard-coded exposures. So here's a visualization of the simulated toy causal system. The system stochastically models an individual's outcome of myocardial infarction, or MI, according to their exposures, which include obesity, sedentary lifestyle, high LDL cholesterol, and family history. So by design, high cholesterol is sort of a true causal exposure of MI because it has the highest risk with a probability of 0.03. But in this toy system, there's also something that is known as a backdoor path between high LDL and MI that goes through obesity and sedentary lifestyle. A backdoor path is a non-causal pathway that can obscure the true risk of 0.03 that we know exists in the data. So after generating the data for the simulation, I restricted the data that was available to us to support running two models. The first was the censored model, where the backdoor path is not observed and only high LDL family history and myocardial infarction are available to us. The second model is the uncensored model, where everything is available to us. I can then compare the risks of high LDL under both of these models, which can provide a means to not only assess the correctness of implementation of NORA, but can also be used to permit a comparison with logistic regression about which model is less biased when the knowledge of the causal graph, that backdoor path, is actually infeasible. So when looking to assess the correctness of implementation, we look to recover that true attributable risk of high LDL within a very small margin of error. And as you can see in this table, with all the data available, NORA was able to recover this with near perfect precision. So if we turn our attention to sort of this robustness to bias, we use the results above to calculate a % discrepancy from both models under both censorings. And I want you to note here that NORA is less biased when backdoor paths were both observed and unobserved versus the logistic regression. In the second sub-aim of 3, AIM 3B, I applied NORA to observational data sets. And this aim addresses whether or not NORA can be used to support high throughput attributable risk estimation from real-world clinical data. So to determine NORA's utility in practice, I applied the model to observational cohorts that were curated to look at sort of a single outcome. And you can see in the table on the right, I looked at a variety of different relationships. Some of these I'm going to go into in greater detail later, but for example, look at the outcome of heart failure. This is a condition-condition relationship because heart failure itself is the outcome as a condition, and when I pre-processed this, I was looking for other conditions that happened before to be our exposures. I then applied NORA and the comparators, which included the Levin calculation, approximation by disproportionality methods, including the MGPS and RR, and penalized logistic regression, specifically L1. And I did this to identify high AR exposures and their estimates from these causal systems that are listed here. So ideally, I would be interested in comparing NORA's performance to the gold standard, but in this case, the gold standard is an experiment, which is infeasible to execute anew for every exposure outcome pair. So in order to best evaluate the model for estimating attributable risks, I actually dovetailed off that global local inferences that were desired in the AR model that I mentioned throughout the talk earlier today. First, I evaluate the global inferences of the risk of NORA by comparing high attributable risk exposures from NORA versus the high attributable risk exposures from the comparators that I mentioned. And I did this by looking at our model's AR estimates versus the literature. And today I'm just going to be presenting Kaposi sarcoma as the outcome of interest. Secondly, I evaluated local inferences, but I did this in two parts. The first part was local inferences of the outcome by seeing how well NORA and L1, which was the only comparator method that can actually support this kind of evaluation, how well these two methods can predict the outcome for an individual given their exposure and the learned attributable risks. And we do this with the area under the receiver operating curve, or the AUROC. The second part of this looks at local inferences of the risk. And this is very similar to the global inferences of the risk, but it takes place over an individual in which exposures may actually vary. So in practice, I did this by creating a simulation excuse me, in which I drew activations based on the individual's exposures and learned attributable risks for those exposures. And then we can best rationalize which exposure has the highest AR for this particular patient. And I'm going to present an analysis of this for one heart failure patient today. So Kaposi sarcoma is a very rare kind of cancer that is most commonly seen in HIV and AIDS patients. And if we take a look at the ARs that were estimated by NORA and all the comparator methods, we see this really wide range. But because this relationship between Kaposi sarcoma and HIV that I mentioned is really well defined and really well understood, we actually have a gold standard estimate, which is 0.0048. And of all the models that I implemented, NORA is not only the closest, but it's the only one with an appropriate order of magnitude. And these results demonstrate that when making inferences of risks of exposures over the whole population or globally, NORA outperforms. So moving on to the local inferences of the outcome, I took a held out data set from our outcome defined cohorts that were on the screen here, and I sought to predict whether or not those patients would get the outcome based upon the exposures and the attributable risks learned by these models. This exercise is really only feasible to implement for NORA and L1, so other comparator methods are just going to be put aside for the moment. So for each cohort, I calculated the AUROC for both NORA and L1. And as a reminder, a higher AUROC means that this is better at predicting the outcome. Here, I've highlighted the best performing model in each cohort scenario. And superiority of performance was really mixed. NORA just edged L1 out in the number of cohorts it did best in. But nonetheless, I think this is compelling evidence that NORA at least performs comparatively well to L1, which is the default model for this kind of task. And finally, I evaluated the local inference of the risk. And this is really more a demonstration of how you can use NORA to explore risks for an individual, which you cannot easily do with any of the other comparator models I mentioned. So I took a random heart failure positive patient from our cohort, and I used their personal exposures and the model's learned attributable risks to simulate whether or not the exposure was activated for the outcome. And over all the simulations, I calculated the proportion of time that the exposure was active, which gives us an estimate of AR for this particular patient. So here are those results. And you can see that for this heart failure patient, the exposure with the highest AR were cardiomyopathy, coronary arteriosclerosis, pre-infarction syndrome, all of which have very, very clear relationships with the outcome of heart failure. Though other exposures do exist, such as abdominal pain and gout, these have an AR of 0 for heart failure, which is absolutely appropriate. These results demonstrate how the model supports inferences of risks for an individual given global risks and personalized exposures. Of course, as with the other, there are limitations with this aim. Of principal concern is the model's performance when the causal independence assumption is not met. The model is also Bayesian, meaning that we make certain choices about the shape of the distribution, which could be wrong. And in this analysis, particularly in aim 3B, we may not recover true causal factors, but rather instead may be learning patterns of EHR documentation. So timestamps are especially concerning, since temporality is really the only real assumption of causal relationship that must be true. Additionally, estimates of risk could be confounded by unseen exposures. I believe that this dissertation provides a significant and valuable contribution to the scientific community. So a number of techniques exist to improve and support causal estimates from observational data, but at present there's really no widely used framework to evaluate modeling assumptions relative to experimental data. In aim 1, I showed that RCTs, which we accept to be sort of the least biased source of causal knowledge, can be compared to gold estimates generated from observational data and thus provide a methodology to assess the validity of causal claims and a platform with which to evaluate inference methods. However, in this aim, I additionally showed that fundamental differences exist between RCT populations and real-world cohorts, and that exist and persist despite the application of eligibility criteria. Excuse me, this may have a result in a failure of replication, which has really grave impact for the practice of evidence-based medicine. In aim 2, I presented the CGAN, which is an effective method to support natural experimentation. The application of the model to real-world data could provide an alternative means to causal inference from observational data sources. Furthermore, if we assume that all potentially confounding variables are observed and included as features in our model, the superiority of the CGAN in learning balancing weights suggests that the average treatment effects born from CGAN-weighted cohorts could be less biased than those estimates generated from traditional weighting methods. And finally, in aim 3, I presented NORA. The model identifies a cohesive set of high AR exposures when causal graph construction is infeasible. The simulation I presented today suggests that the model may be more robust to confounding than logistic regression. And finally, unlike comparator methods, NORA supports global and local inferences, which help us rectify care of a single patient with public health. Critically, the methods in this dissertation may increase the confidence of claims from observational data and may permit the efficient identification of effective interventions and improve outcomes. This research was funded through the National Libraries of Medicine with the grant numbers that were shown on the screen. The references are available by QR code for anyone here who's interested in them. And before I end, I would very much like to take this time and acknowledge my advisor, Dr. Adler-Parat, my committee members, Dr. Wen, Ryan, Ranganak, and Goldsmith, my co-authors and collaborators over the years, my colleagues at DBMI, but especially those that are mentioned on the screen, and of course, my friends and family, but notably my mother, Constance Salemi, and my wonderful husband, Evan Jordanella. And with that, I would like to thank you all for your time, and I'm very happy to take questions.
Thank you, Amelia. Let's give Amelia a round of applause. and we have a few minutes. Now we are open the floor for questions from the audience.
Or maybe you could chat it if no one wants to enable video.
Yeah, people can also type in their questions in the chat box. We have a couple minutes. Yeah.
While we're waiting for folks to comment, Amelia, I want to congratulate you on an extraordinarily clear presentation. I think you've provided a role model for all of our students to be able to walk through very eloquently all of your material. And so I want your friends and family to know that this is not how all PhD presentations go down. This was an extraordinarily clean and well-versed presentation. So from a communication perspective, it's really spectacular. So great job.
Yeah, and I remember over the years, Amelia has won multiple best presentation, best poster presentation, and paper presentation in different conferences. Indeed, this is very clear and very logical.
Thank you.
Any questions from?
Come on, some friend or family has to stump her with some hard mathematical question.
I think everyone is stunned.
I think everyone's like midday, kind of overcast in quarantine, an hour of talking about science. Let's see.
Adler, I think if we don't get questions, then maybe we can give Amelia 1 or 2 minute break, and then we will switch to a closed session, right?
That sounds great.
Yeah. And thank you all for attending. And next we need to close for the committee discussion. Thank you all.